class. Today we will study the topic related to electrochemistry. Now, electrochemistry is defined as the study which deals with interconversion of electrical energy and chemical energy. Electrical energy is because of the movement of electrons which produces current, and that current can be utilized in doing electrical work, and this electrical energy can be produced from some chemicals. So what is happening, that chemical energy is converted into electrical energy, or sometimes backward reaction is also possible in which electrical energy converts into chemical energy. For example, recharging of batteries. So these kind of studies are done in electrochemistry. Now, what are electrochemical processes? Electrochemical processes are actually redox reactions, combination of reduction and oxidation. And what happens in redox reaction? Energy is released either by a spontaneous reaction. Well, spontaneous reaction is a reaction that happens on its own without utilizing any external energy. So if it is a spontaneous reaction, energy is released and there is interconversion between electrical and chemical energy. So this happens in electrochemical cell or galvanic cell or voltaic cell. Meaning to say, there are two kinds of electrochemical processes. A process in which spontaneous reaction occurs and electrical energy is produced from chemicals or chemical energy. This is known as galvanic cell. And the cell in which the opposite reaction happens, that in which electrical energy is used to carry out a non-spontaneous reaction. A non-spontaneous reaction is a reaction which cannot happen on its own. We have to give energy to carry out this reaction. So if a chemical reaction happens, this kind of non-spontaneous reaction happens, then this is known as electrolytic cell. So there are two kinds of electrochemical processes which we are going to study in electrochemistry. One that takes place in galvanic cell by utilizing spontaneous reaction, and the other that takes place in electrolytic cell by utilizing uh, electrical energy to carry out non-spontaneous reaction. And this electrochemical process that takes place in electrolytic cell is also called electrolysis. We will study electrolysis later on. But let me just give you an idea what is reduction and what is oxidation. Okay, if you look at the reaction below, magnesium is reacting with HCl to give magnesium chloride and hydrogen gas. Magnesium in its pure form, metallic state, is zero. No electron is lost or gained by magnesium in this state. And here in HCl, hydrogen has +1 oxidation state. So in the products, magnesium chloride is formed, and here the oxidation state of magnesium is +2. If you look at chloride, it has 2, so it is -2. To balance it out, to neutralize it, magnesium will be +2. So what is happening? The oxidation state of magnesium is increasing. So this is the process of oxidation. Oxidation is defined as the reaction in which there is increase in oxidation state by losing electrons. Magnesium has to lose electrons to get to +2 state. It has to lose 2 electrons. Now if you look at here the second product, which is hydrogen, hydrogen oxidation state is 0. Hydrogen gas, all the gaseous forms of elements have 0 oxidation state. So here hydrogen is +1 and it is changing to 0. There is decrease in oxidation state, which is called reduction, and reduction happens by addition of electrons. So hydrogen is gaining electron hairs to undergo reduction, and magnesium is losing electrons here to undergo oxidation. So this is an one process, an example of a process in which both oxidation and reduction are taking place. Actually, all the reactions, normal chemical reactions in which electrons are involved, always there is a gain of electrons by one species and loss of electrons by another species. That is the main thing that happens, that transfer of electrons between two species takes place. So look at the beaker here. Suppose we have a piece of zinc metal. If you look at the beaker here, and we have a piece of zinc metal, the metal bar, and is dipped in a blue solution. This brown bar is zinc metal and that is dipped in a blue solution. Blue solution is copper sulfate. Copper sulfate is blue color because of copper plus 2. So after some time, what happens if you look at the second beaker? That is after some time. If you see all the brown stuff that is present on this metal bar is going inside, what you can see here, and the blue color has disappeared. So what does it show? That something is happening between this beaker water solution and the zinc bar. Some reaction is going on. Actually, what is happening? The zinc is corroding and dissolving into the solution. Zinc from the metal bar is going into the copper sulfate solution, and here the zinc metal is changing into zinc plus 2 state. This brown color molecules which you will see in this solution are zinc plus 2. So zinc metal is changing to zinc plus 2, oxidation is taking place, and on the other hand this blue color is disappearing. It means copper plus 2, the color of the solution is blue because of copper plus 2. The copper plus 2 is changing to copper solid. This red ball is representing the copper solid. So copper plus 2 is changing to copper solid, and in copper solid metal, and zinc solid is changing to zinc plus 2. So what is happening? Simultaneously, oxidation and reduction is taking place in this system, and because of that, when blue color is disappearing, it means copper plus 2 is reducing to copper solid, and this brown color on the metal is disappearing. It means zinc solid is changing to zinc plus 2. So what is happening? Transfer of electrons taking place between zinc and copper, right? Transfer of electrons. So if we allow this transfer of electrons through another route, for example a wire, rather than in the same system, if we allow or channelize these electrons to move in a particular path, for example in a wire, then this will be known as flow of charge through a certain point per unit time, which will be called current. Current is because of movement of electrons. So that's what we do in electrochemistry. We carry out the oxidation reduction process and give these electrons a separate route, and the same reaction happens but in a different style. If you look at the figure here, this is the same setup previously, but the zinc bar and copper solution are separated this time, and they are connected by a wire. See here, this is a zinc anode, a zinc electrode, or you say zinc bar initially. We will define these terms later on. So this is a zinc bar here, okay, and it is dipped in an electrolyte solution, some salt solution. For example, zinc sulfate. Any bar, any metal which with a solution having a common ion. I mean to say that it is zinc bar, so the solution is zinc sulfate or any other zinc chloride, but it has to have zinc cation, which is common with the metal from this bar. Similarly, here there is a copper bar and it is dipped in copper sulfate solution. Copper ion is common. So this time we have added different solutions, electrolytic solutions, to the separate beakers, and then these zinc bar and copper bar is connected through a wire. You can see this wire, and even you can see the flow of electrons here. Because zinc is oxidizing, as I have discussed earlier, and is losing electron, zinc plus 2, so electrons are moving from zinc side. So the arrow is from this side to this side, and copper is accepting electrons, so the electrons have to come to the speaker since it is a carrier. So the same process is taking place, and what is happening on this side, on the zinc side, zinc is oxidizing. You can see the oxidation reaction here. Zinc is changing to zinc 2 plus along with removal of 2 electrons. Or if you look at the magnified picture, zinc, this is coated on this bar, and it is changing to zinc 2 plus and then entering it to the solution. The zinc 2 plus, when it is formed, it will not stay with the bar, actually it will come into the solution. So that's why zinc 2 plus are shown here downward inside the beaker. It means they are part of solution now. And on this side, what is happening, you can see that there is a copper bar. Copper bar means that uh, first electrons come here inside this solution, and they react with copper 2 plus to give copper solid, and this copper solid is actually depositing slowly on the surface of this electrode. So if you carry out this reaction, and after some time, if you measure the weight of these bars, what will happen before reaction? If you measure the weight of the zinc bar, this bar, and after reaction it will decrease. The weight will decrease after the reaction for the zinc bar, because the zinc has been uh, detaching or eroding from the zinc metal bar and is coming into the solution. That's why its weight will decrease. While on the other hand, if you check the weight of this copper bar later on, so it will increase because more copper is depositing on its surface. So after this reaction happens, the weight of this bar, copper bar, will increase. So this is one way to note what is happening in the electrochemical cell. So on this side, oxidation is taking place because the weight is decreased. On this side, reduction is taking place because the weight of the bar is increased. Now I will use officially some different terms for the bar. Instead of saying bar, I would call them electrodes. Here we have the zinc electrode, and on this side we have copper electrode. Electrode is a kind of metal bar where either oxidation or reduction takes place. So the electrode at which oxidation takes place, this is known as anode, and the electrode at which reduction takes place is known as cathode. You can see the zinc anode written here and copper cathode. Because always remember that any electrode where oxidation takes place, this will be designated as anode, and any electrode where reduction will take place, this will be designated as cathode. And since electrons are moving from anode, so this side will be negative, anode will be negative, and electrons are entering into copper side, so this side will be positive, because electrons are moving from a region of higher potential to a region of lower potential. Higher potential is where there is increase of electrons, electron rich area, and lower potential where there is deficiency of electrons, electron deficient area. So that's how when electrons will move, circuit is completed, and these electrons are actually causing electrical energy, and that electrical energy can be used to light a bulb, for example, that is shown here. So if you look at the overall reaction, zinc solid plus copper 2 plus, it is giving you zinc 2 plus plus copper solid. This overall reaction is a combination of individual reduction and oxidation reactions. Okay, in this diagram, this is there is another weird thing. There is a U-shaped tube in inverted position and is dipped. One part of it is dipped in copper solution and the other part is dipped in zinc solution. And what's the purpose of that? Well, there is a significant role of this inverted tube, and this inverted tube is called salt bridge, or there's a name for it. It is known as salt bridge, and it contains some uh, inert electrolyte, for example, potassium chloride. And the purpose of this salt bridge is to neutralize the net positive charge or net negative charge in these beakers. What do you when I say neutralize? What does it mean? It means if you see that without using the salt bridge, what happens when zinc is converting to zinc 2 plus and is accumulating in the beaker, there will be increase of positive charge. Zinc 2 plus is cation, positive charge, so it is increasing in this side, on this side, in this solution. There will be more positive ions as compared to negative ions. Which are negative ions here? Sulfate. Sulfate ions are also in this portion along with zinc 2 plus. But sulfate ions, number of sulfate ions is constant, and more zinc is entering in zinc in the form of zinc 2 plus in the solution, so there is increase in zinc 2 plus. So what is happening? There is accumulation of positive charge here. Similarly, on this side there is accumulation of negative charge here. Why? Because initially we have copper 2 plus and sulfate 2 minus ions. What is happening? Copper 2 plus is decreasing because it is undergoing reduction to give copper solid, and that copper solid is being attached to copper cathode. So what is happening? The copper 2 plus is disappearing, so increase in negative charge. Increase in negative charge on this side, increase in positive charge on this side. When this happens, so neutrality is disturbed. So if neutrality is disturbed, then electrons won't move from anode to cathode. They will not move because since positive charge is here, why electron will move here? It will try to stay here to compensate for this charge. So in order to carry out this electrolytic process, this movement of electrons, we need to keep the charge neutralized on both sides every moment. During the course of this electrochemical reaction, we want to keep the charge neutral. So what happens? We insert this salt bridge and the sides of the salt bridge are made porous. It means the ions can uh, come outside and they can enter in these solutions. They can travel. For example, if positive charge starts building here, zinc 2 plus increases, what will happen? The chloride, potassium chloride here is here. The chloride will move here and will enter into the solution through this membrane or through this cotton plug. This is a sort of membrane, and it will neutralize or it will balance the positive charge because there is a positive charge, and to balance it out, the negative charge will flow here. Chloride will flow here. So as many the number of zinc 2 plus are produced, so that many chloride ions will travel and come into the solution to neutralize it. So as a net result, the solution here will be neutral. There will no accumulation of positive charge. Similarly, on this side, to balance for copper 2 plus, or because copper 2 plus is disappearing here, so to we need positive charge here. That positive charge is provided by potassium plus 1, and it will uh, travel through this membrane and enter into the solution. So the purpose of salt bridge is to neutralize the solutions here, or to prevent the accumulation of positive and negative charges here, or to continue the flow of electrons in this electrochemical cell. So here I have given the same half cell reactions. Individual reactions For example, individual oxidation reaction and individual reduction reactions, these are also known as electrode half cell reactions. So individual electrode half cell reactions are given here, and if you combine them, you will get something like this. This is the full reaction, this is the net reaction, and this is the uh, anode half cell reaction, this is the cathode half cell reaction. Class, we have observed that in galvanic cell, electrons flow spontaneously or naturally from anode to cathode. And as I mentioned earlier, that at anode there are electrons rich. It is it is an area with more electrons, and then cathode is electron deficient area. So kind of a potential is established, uh, and anode will be at higher potential where there is excess of electrons, and cathode will be at lower potential where there is lack of electrons. So that's why electrons flow naturally or spontaneously from anode to cathode. This is just similar to the uh, water direction in a waterfall. In a waterfall, water flows downwards, which is because of the gravitational potential energy. You know that because of the gravitational force, all the things they fall towards the earth. And setting this gravitational force as a reference, the things which are near to the earth are at lower gravitational potential energy, and the things which are at a higher distance or away from the earth will be at higher potential energy. Potential energy means energy due to position. At higher level from the earth, it will have higher gravitational potential energy. So water also flows based upon this potential. So there are movement of electrons is also because of some potential between the electrodes. So this potential is called cell voltage or even cell potential, or there is another name for it which is known as electromotive force. It is not a force like F is equal to ma, but this is more like a cell voltage or another name for cell potential, because it drives the electrons from anode to cathode. It is the cause of movement of electrons, so that's why we kind of name it as force or electromotive force. So it is more like a voltage or potential. Now, this potential or cell voltage depends upon different factors, including nature of electrodes, what is the nature of the electrode material, and the nature of ions. You have seen the example of zinc and copper. And it also depends upon concentration of ions. More the number of ions, higher the number of ions, there will be movement of electrons will be for a longer period, and then that will be responsible for producing electrical energy. And then there is another factor, temperature. Temperature is also important. It affects the movement of electrons. So indirectly that is related with cell potential, or cell potential depends upon temperature. Usually at low temperature, movement of electrons is less, and so cell potential will be less. And higher temperature, movement of ions is or electrons will be more, and so electromotive force or cell potential will also be greater. Now, if you look at this diagram here, it is the same diagram for galvanic cell, but there is some kind of meter inserted in between the flow of electrons, and it's showing some reading. So this is known as voltmeter, digital voltmeter, and actually it measures the potential between anode and cathode. And here it is giving a reading of 1.10 volt. This is particularly for zinc and copper galvanic cell system. When we have zinc coupled with copper, the overall cell potential is given by this voltmeter, and it is 1.10 volt. Okay, now I have given this phrase here, cell diagram. What does it mean? I don't mean this diagram, Actually, it is a way of representing galvanic cell in this way. If you see here, um, it shows that zinc solid, this is for this electrode, which is anode. It is representing this electrode, zinc electrode here. Then it is in contact with zinc solution, which is zinc sulfate. So we are just representing the common cation. We don't care about sulfate. It could be chloride or any other anionic solution coupled with zinc. So zinc, that is coupled with zinc 2 plus solution. Now this bar represents the phase boundary. The single vertical line is showing the separation between these two phases. One phase is the zinc solid and the other phase is zinc liquid. Since they are different phases, so we have to show some kind of separation between them, and that is represented by this vertical line. Then zinc 2 plus is there, and then we have to mention its concentration. This is important since the cell voltage depends upon concentration of ions. So we have to write down the concentration. Suppose it's 1 molar, zinc sulfate solution is 1 molar, so we will put in parenthesis the concentration 1 molar. So we have to put the parenthesis. It is uh, what you call it is the standard way of writing this cell diagram. And then there is double vertical line. There are two lines, and these two lines are for what? This salt bridge. These two lines represent the salt bridge, and then the next one is copper 2 plus solution. If you see, if you go from this side, if you start from this side, first we have zinc electrode. It is in contact with zinc solution. Their zinc solution is in contact with salt bridge, and their salt bridge is in contact with copper solution. So in just like given here in this diagram, we have to represent it with the same sequence. We have to write it with the same sequence, that salt bridge and then copper solution come, and then that copper solution is in contact with copper electrode. So we write this copper electrode, which is solid, at the end. So we start from anode, then one by one, whatever comes in contact with it first, we write that. Then salt bridge, then that salt bridge comes in contact with copper solution, copper 2 plus copper sulfate solution, for example. Then we also have to mention the concentration of electrolyte on this side, and then that is in contact with the last electrode on this side. So we start from right side, from anode, and we end up at the left side, which is cathode electrode. So this is called cell diagram. How to represent a galvanic cell? So if I just write down this small this line, this representation, it is good enough to explain what kind of electrodes I am having and what concentrations are there, what kind of electrolytes are there, and I can draw this diagram. Instead of making this huge diagram, I can just briefly concise it into this one line, one representation. Okay, what else? So we have to move from left to right. If you take it as a left, then we have to move from left to right, or moving from anode to cathode. Or you can just keep in mind that you can start from anode and go to cathode. Here you can see a real-time picture of a galvanic cell based upon copper and zinc that is assembled in lab. You can see these two beakers. One is zinc sulfate solution electrolyte, and another is copper one. And you can see they are connected, both of these are connected with a huge box, and this huge box is just a voltmeter and is giving a reading of 1.10 volt. It means for this copper and zinc galvanic cell system, the overall cell potential is given as this value here, 1.10 volt. This is the E cell. This is the overall cell potential of this galvanic cell. It means it consists of the individual cell potential of both electrodes, copper and zinc. And if the concentration of copper and zinc is 1 molar, and system is the system readings are carried out at 25 degrees centigrade, then these are standard conditions. If the concentration is 1 molar and the temperature of the galvanic cell is 25 degrees centigrade, then these are standard conditions. And then at this time, the E cell will be represented as E naught cell, or standard cell potential. Here you can see this formula. Naught represent the standard conditions, and E cell is the overall cell potential, overall standard potential of this system, which is given here for copper and zinc, and it is given by a formula which is E cell is equal to E cathode minus E anode. It is the difference of the overall cell potential is the difference of cathode potential minus anode potential. So this is the standard formula for standard E cell, E naught cell. Or you can say that overall cell reaction is the sum of two half cell reactions. The overall cell potential is the sum of two electrode potentials. So we can measure the overall cell potential as this digital voltmeter is giving the overall cell potential reading of 1.10 volt. But can we measure the absolute single potential of individual electrodes? The answer is no. We cannot measure the E cathode separately or E anode separately. Or we can say that we cannot measure the absolute potential of each electrode. We can only see the value of overall cell potential. So then it becomes difficult if we want to measure the potential of a single electrode. But there is a way to do it. What we can do, we can take, or we can set the potential value of one of the electrodes as 0. For example, E cathode, we take it as 0, or we take E anode as 0. Then we measure the cell potential, and in this case we have one value, one of these values 0, and one of these E cell is known. So we have one value 0, one is known. Then we can find one of the unknowns, either E anode or E cathode. And when we the electrode for which we set the value of potential equal to 0, this is known as standard electrode. We set it as a standard. When we take the potential of one of the electrodes as 0, we name it as standard electrode. And we cannot use any metal as standard electrode. We use usually hydrogen electrode as a reference, and we use it as a standard electrode. And we carry out the reaction at standard conditions, so we name it as standard hydrogen electrode. If you see in this diagram what is happening, there is a metal bar, and this metal bar is inside a glass tubing. And the metal bar is made of platinum electrode, and outside this glass tubing it has an inlet for introducing hydrogen. So hydrogen gas is introduced at 1 atmospheric pressure, which also denotes the standard condition, 1 atmospheric pressure. And this whole setup is carried out at 25 degrees centigrade. This is another standard condition. And then this platinum electrode along with this tubing is dipped in 1 molar HCl solution. We have to take a common ion. As I told you earlier, for hydrogen gas, the common ion is H+. So H plus along with Cl, hydrogen chloride, with concentration of 1 molar is taken here. So all these standard conditions are maintained, and then hydrogen is passed through this inlet at 1 atmosphere. And what happens, the hydrogen is exposed to this platinum electrode, or we say otherwise, the platinum bar or electrode is exposed to hydrogen when hydrogen passes through this inlet. So this is the representation of standard hydrogen electrode, where hydrogen gas at 1 atmosphere is bubbled through 1 molar HCl solution. So what happens What we do now, we have two things which can be reduced and oxidized at standard hydrogen electrode. One is hydrogen and the other is H plus ions from HCl. So both type of reactions are possible. If we see the dissociation of hydrogen, hydrogen can dissociate into two hydrogen ions with the removal of two electrons. It means hydrogen is getting oxidized with the removal of electrons. Here hydrogen is 0, here hydrogen is plus 1, proton is plus 1. So hydrogen can be oxidized and the product is H plus ions. Dissociation of hydrogen can take place on the surface of platinum electrode. That's why we have platinum electrode which can act as a catalyst, and it provides a surface as well as it acts as catalyst for dissociation of hydrogen. But as I said before, there is another reaction that can take place in standard hydrogen electrode, and that is reduction of hydrogen ions. If you see here, these hydrogen ions can be reduced by two electrons giving hydrogen gas. This is also possible at She electrode. So now the question is whether both reactions are taking place. No, it depends upon the second partner which is attached to standard hydrogen electrode, that which reaction will take place. If the second partner is acting as anode, oxidation taking place, then at She reduction will take place. If the second partner is the cathode, reduction is taking place there, and then at She oxidation will take place. Opposite reaction will happen at She. You have to keep that in mind, that opposite reaction will take place at She electrode. So, and particularly for this reduction reaction of hydrogen ions, when two electrons are combining with hydrogen ions and they are getting reduced to hydrogen gas, particularly for this reaction, the standard electrode potential is set as 0 volt. Since this is a reduction reaction, this is an oxidation reaction, this one, and the lower one is a reduction reaction. Particularly for a reduction reaction, if it is taking place at standard conditions, then this is known as standard reduction potential. What we call it? Standard reduction potential. We use the word reduction because here for this reaction the reduction is happening. So standard reduction potential for of She is 0. You have to keep it in mind. Now again, this is the same thing, that this sign degree is for standard conditions, and the voltage associated with standard conditions which are 1 molar, and the hydrogen is gas pressure is maintained at 1 atmosphere. These are standard conditions, and the temperature is also 25 degrees centigrade. I have not written here, but you can add it that temperature is 25 degrees centigrade. All three conditions are standard conditions, and standard reduction potential at these standard conditions is set as 0. So this She can be coupled with other metal electrodes, and we can find the absolute potential of other metal electrodes. For example, we want to measure the absolute potential of zinc metal. But before we go into details, I would like to add here that this formula for E cell, which is equal to E cathode minus E anode, here these values E cathode and E anode are given in the form of reduction potentials, standard reduction potentials. So using this formula, we can find out the absolute standard reduction potentials, either E cathode or E anode, but these are in the form of reduction potential. So what we are going to do, we are going to find the reduction potential of zinc, standard reduction potential of zinc, which is single electrode. This is one example. So what we will do, we will couple it with She. Here, if you can see in this diagram, the zinc electrode is coupled with She. So now any reaction oxidation or reduction that is happening in zinc will dictate the opposite reaction happening in She. What I mean to say is that if oxidation is taking place here, then opposite reduction will take place at She. Or if reduction is, if reduction is taking place, then at She uh, oxidation will take place, or she will behave oppositely according to the another electrode coupled with it. Okay, here in this case we have zinc. What we do, we first, before putting it in the galvanic cell system, we measure the weight of this zinc bar. Zinc electrode, we measure the weight before start of the reaction, then we insert it and we couple it with the She electrode and we maintain the standard conditions, and we insert a voltmeter inside to measure the E cell, and then we let the reaction, electrochemical reaction, go on in the galvanic cell. And then when the reaction is finished, what we do, we stop it, we take this zinc electrode out and we measure the weight again for this zinc electrode. Why we want to measure the weight? We want to see if the weight is reduced as compared to the initial value, then definitely oxidation is taking place here. If the weight is increased after the reaction, then it means reduction is taking place, because when oxidation is taking place, zinc from the zinc electrode is dissolving into the solution. So what will happen, it will decrease the weight of the this zinc electrode after the completion of reaction. But if reduction is taking place, then more zinc will be attached to this electrode and there will be increase in mass. So but in this case, what we see, there is decrease in mass of zinc electrode after the reaction. So it shows that at this side oxidation is taking place. So zinc is getting oxidized by this reaction. And if we represent this picture in form of cell diagram, it will be given as here. It is coupled with She electrode. Zinc solid is in contact with zinc 2 plus, which is this electrolyte, and the concentration is 1 molar. We have to maintain the standard conditions, and that is in contact with salt bridge, and then hydrogen ion HCl solution, which is 1 molar, then that is in contact with hydrogen electrode. We also have to take care of platinum. So here we represent two things uh, at the this side, hydrogen gas along with this is in contact with platinum electrode. We have to mention both of these components, hydrogen gas and platinum solid. So what I was saying is that because of the decrease in mass, we could guess that oxidation is taking place here. So that's why we have placed zinc on this side. This is the anode place. This side is anode place and this side is cathode place. So now in the presence of zinc, what will happen? She will behave as cathode. Reduction will happen here. So if we look back at this reaction, in the presence of zinc, what will happen? At She, this reaction will take place. That is, hydrogen ions will be reduced to form hydrogen gas. And during the reaction, we will see that you can see in this diagram these bubbles. The bubbles are coming out. These bubbles are actually representing the production of hydrogen, which is because of this reaction. Because at zinc, oxidation is taking place, 2 electrons are being received by this hydrogen and more hydrogen gas is produced at cathode. Okay, then we also measure the cell voltage. We have inserted the voltmeter inside and we see that the value comes out to be 0.76 volt. So for here, E cathode is She and its reduction potential is taken as 0 volt. Okay, and we have measured the E cell from experiments, which comes out to be 0.76 volts. So if we know 0.76, we know this is 0. So we can find easily the anode, E anode, which is the zinc reduction potential of zinc. So you keep in mind that these values are only reduction potentials. E cathode and E anode are given in the form of reduction potentials for reduction processes. We have to look at the reduction processes. So here, this E anode, according to this formula, this E anode for zinc will be given in form of reduction process, reduction potential. As you can see here on this slide, we can write the half cell reactions for zinc. This is oxidation reaction for She, which is at the cathode. This is the reduction reaction. And the overall reaction is zinc plus 2 hydrogen ions. This is from HCl and it is giving zinc 2 plus at one side at anode compartment and hydrogen gas bubbles at the cathode compartment. So inserting these values in this formula, as I said, E cathode, which is here hydrogen, this is set as taken as 0 minus, this is the reduction potential of zinc, which is given here. So this is equal to minus 0.76. This minus can be shifted here. So reduction potential of zinc is, standard reduction potential of zinc is given as 0.76 volts. This is so easy. Just by setting one of the values as 0, we can find out, or we can figure out the second value from the overall cell potential. Okay, the same thing we can do for copper electrode. We can measure its standard reduction potential by coupling it with She. Now we will do the mass measurement, weight measurement before and after the reaction for copper electrode. And here in this case, the copper weight of the copper electrode has increased after the reaction. So we assume that reduction is taking place here. More copper is depositing on the surface of the electrode. So in this diagram, you can see that the She is on left side, in this side, at anode side, and copper electrode is on the cathode side. It means in the presence of copper, what is happening? The She is behaving as anode. But previously, what we see that in the presence of zinc electrode, She was behaving as cathode. So it's a different. The other counterpart dictates how She will behave. So in this case, in case of copper, what is happening? We can see that copper is getting reduced. Why? Because the weight of the copper has increased after electrode has increased after the reaction. So copper is getting reduced in this. This is given by this equation, and the cell diagram we can denote it in the presence of She. We will start again from this side. From left side, we have platinum solid that is in contact with hydrogen gas, which is maintained at 1 atmospheric pressure. That is in contact with hydrogen plus in the form of HCl. So we just write H plus and its concentration is 1 molar, and through a salt bridge, which is double vertical lines, this is in contact with copper solution, which is copper 2 plus, and its concentration is also maintained at 1 molar, and that is in contact with copper solid electrode whose reduction potential we want to figure out. So at anode, She is there, hydrogen will dissociate into hydrogen ions. Now this reaction, as I said earlier, that both type of reactions, oxidation and reduction reactions, are possible at She. So here oxidation reaction, we will write down that hydrogen is dissociating into hydrogen ions with removal of 2 electrons, and at cathode copper is getting reduced, and we can add up these, and we can use the same formula, E cell is equal to E cathode minus E anode, to calculate the reduction potential of copper, standard reduction potential of copper, which comes out to be 0.34 volts. This is positive value for copper. Reduction potential of copper comes out to be plus 0.34, whereas for zinc it was negative 0.76 volts. So it means it can exist in, reduction potentials can exist in two values, negative or positive both. Negative means the reaction is non-spontaneous in way of reduction process. As a reduction process, it is non-spontaneous, but as an oxidation process, it is spontaneous, because if we inverse it, its reduction potential will be inverse with positive sign. So this reaction is possible in this direction, but other way it's not possible. Other way, its reduction potential will be minus 0.76 volts. So we have calculated the standard reduction potential of copper and zinc by coupling them with She electrodes. So what we can do now, we can add these two, the anode oxidation reaction of zinc and cathode reduction reaction of copper. We can add these, And we can also add the cell voltages, standard reduction potentials of these two electrodes, and we can find out the E cell. So by adding the E cell of copper, which is 0.34 volts, and by inserting the value for standard reduction potential of zinc, which is minus 0.76 volt, the E cell comes out to be 1.10 volts, which is same as I have shown you guys earlier. You can see in this diagram, this is 1.10 volt, and that is for, taken by coupling copper with zinc system. So in this way, what we can do, we can measure the standard reduction potentials of different metals other than copper and zinc, and at standard conditions, and we can find out their reduction potentials. So if you see on this page, this yellow table, the reduction potentials of different metals have been tabulated here, have been given here at standard conditions. Scientists have worked out different kinds of metals, not even metals, but other different elements, and they have formulated a table of reduction potentials at standard conditions. And if you see here, the sequence is very important. It is written in a specific sequence. If you see in the middle, this red reaction is for hydrogen. This is a standard reduction potential of She electrode, and its voltage is taken as 0. And above this 0, the standard reduction potentials are positive, and below this 0, the standard reduction potentials of different elements are negative. So what does it show? It shows that all the elements which are above these this hydrogen, they will have positive values of reduction potential. It means they can easily get reduced in presence of hydrogen. That's why you see, we did it with copper. uh, let me check. Yeah, this reaction, copper 2 plus plus 2 electrons. For this reaction, the standard reduction potential we calculated was plus 0.34. So when we couple it with hydrogen, its standard reduction potential is more. For copper, it's 0.34 volts, so it will get reduced, and hydrogen will get oxidized. But for the elements which are below hydrogen, their reduction potentials are negative. What does it mean? It means that these are they have low reduction potential, so they don't like to get reduced, rather they will get oxidized. When the reduction potential is negative, these elements will tend to get oxidized spontaneously. By naturally, oxidation is more favorable in these elements which are below hydrogen, and naturally or spontaneous reactions of reduction is more favorable in these elements which are above hydrogen. So this is known as electrochemical series. This table, given in the form of reduction potentials with reference to hydrogen electrode, standard hydrogen electrode, this is known as electrochemical series. And if you see at the top, the standard reduction potential is given for fluorine, and this is the maximum value of plus 2.87 volt. What does it show? It shows that fluorine is the element, fluorine gas like to get reduced strongly, or it is a strong, other way we say it is a strong oxidizing agent. It will like to knock out electron from other species and itself get reduced. So with respect to oxidizing agent, fluorine is the strongest oxidizing agent. And if we see at the bottom, we can see lithium. Lithium has the lowest reduction potential, minus 3.05 is a negative value, is the lowest reduction potential for lithium. What does it show? It means that lithium does not like to get reduced. It is a strong reducing agent. It's other way around. Strong reducing agent, if it like to oxidize itself and provide electrons to other species so that they can get reduced. you can see this red arrow, red big arrow from bottom to top, and it shows increasing strength as an oxidizing agent. It means that fluorine is the strongest oxidizing agent, and it has, but itself it would like to get reduced. That's why it has highest highest reduction potential. So in terms of oxidizing strength, fluorine is has highest value of oxidizing strength. And if you see this arrow which is going down from top to bottom, it means that strength as an reducing agent is increasing from top to bottom. Reducing strength is increasing from top to bottom, or we say that lithium is the strongest reducing agent. Itself, it will like to get oxidized, and it would like to add electrons to another species, so it is the strongest reducing agent. So that's what these two arrows represent. See, these are just different ways to represent the same thing. Conversely, we can say that fluoride is the weakest reducing agent, and lithium is the strongest reducing agent. Or the other way, we say that lithium is the weakest oxidizing agent, and fluorine is the strongest oxidizing agent. These are just different terms to confuse you, but don't get confused. Just try to understand what these terms mean. Okay, so what is the advantage of getting or having this electrochemical series? Why do we need it? Rather than measuring the absolute reduction potentials of individual elements and then uh, putting them together and measuring the E cell, and if E cell comes out to be positive or negative, we can assume whether the reaction is favorable spontaneously or not. We can just uh, just by looking at this table, we can easily estimate whether the any of the two elements are able to be used to form galvanic cell or not. Rather than doing experiments, we can just guess from the series. How? What we can do, that we say that any species on the left side, that is the reactant side, any species on the left side will react spontaneously with species that appear on the right side. Any species on the left side that are reactant will react spontaneously or naturally with the species on the right side, provided that species is present below. It has to be below the series. For example, we have copper and zinc. If you look at the copper, where is copper? Copper is somewhere with the two electrons is here. Okay, this is copper with electrode potential of 0.34 volts. And we pick another element, zinc. Zinc, its electrode potential is given here. So this it means copper and zinc can undergo electrochemical process, and they can be coupled, and they can be designed in a galvanic cell. They can be put together in a galvanic cell. Why? Because zinc is present below. In this, as I said earlier, the sequence is important. Copper is present above and zinc is present below. Position, we have to check the position. So it means we can easily form a diagonal from starting from copper and going to the reactant side, right side of the zinc, or just by looking at this side. Diagonal can be formed easily from left side, which is copper, and towards the product side of the zinc. This is the diagonal formation. So if you can form a diagonal from left to right side, not from right to left, not the other way. If you can form a diagonal from left to right side, it means the reaction can happen spontaneously. So based upon this diagonal formation, this is known as diagonal rule. Any species on the left of the given half cell reaction will react spontaneously with the species on the right side of the half cell reaction located below it. This is important, it has to be below. Then the diagonal from left to right will be formed. Okay, this is one way by looking at this electrochemical series, or in another way, what you can do, you can add these two values in the formula and see whether the E naught cell comes out to be positive or negative. One point which I didn't mention earlier, I will put up here, that let's go to this page, that we can calculate the E cell for copper and zinc, and it comes out to be, in this case, it comes out to be positive. What does it show? It means that the reaction is favorable in the forward direction. What is forward direction? Forward direction is that zinc is getting oxidized, copper is getting reduced. So the reaction is can happen on its own without the use of external energy. It can happen naturally, spontaneously on its own. More reactants than products will be formed at equilibrium. It also means that, sorry, more products would be formed as compared to reactants when it is positive. But if this value is negative, it doesn't mean that E naught cell will always be positive. Sometimes it is negative. Based upon the values of reduction potentials, sometimes E cell is also negative. When E cell is negative, it means the reaction is not possible spontaneously in the forward direction. It means reaction will not happen and more reactants will be present at equilibrium as compared to the product. I mean, products are not formed, so the reaction is not happening on its own. So from electrochemical series, we can add up the values of these standard reduction potentials, and we can calculate E naught, E naught cell, and we can analyze whether the galvanic cell can be formed or not, whether the spontaneous reaction is possible in that galvanic cell or not. Thing about electrochemical series is that E naught is not affected by size of the electrodes or amount of solution, since it is standard conditions mean it is for 1 mole. For example, if we take the reduction potential of iodine, where it is given here, it is positive plus 0.53 volts. So the E naught is fixed for this reaction. Whether if we take 2 moles, if we take 2 moles of iodine, we will multiply this equation with 2. It means 4 moles, 4 atoms of iodine, and then we have to add 2 more electrons, multiply with 2. I mean 4 electrons will be added and will give you 4 moles of iodide. But the E naught is just for 1 mole of iodine, which is fixed. E naught will remain same, 0.53 volt. You will not multiply 0.53 with 2. You keep in mind that E naught is, of different elements, that standard reduction potential values of different elements, these are fixed. In the numericals, you don't have to multiply with this. If you are multiplying the number of moles, standard reduction potentials, you have to keep them as it is, same as it is. So this thing, and then just like other thermodynamic parameters, for example, change in enthalpy, change in free energy, or entropy, the sign of each can change, but the magnitude will be same. You have seen earlier that uh, this let's see, for zinc, the reduction potential of zinc is minus 0.76. So if you consider this in reverse direction, that is zinc is oxidizing to zinc 2 plus, you put this as a reactant product, that oxidation, if you see it in terms of oxidation, then the magnitude will remain same, 0.76, only the sign will be reversed. Instead of negative, it will be considered as positive for the reverse reaction. So the signs can be reversed, but the standard values are always same for 1 molar. We will not multiply them with a number of moles. As long as they are standard values, they will be kept as it is.